So we started out talking about Lewis theory and ionic compounds, and then we quickly got into the covalent compounds, and now we're going to talk very briefly about bonding in metals. The most straightforward model is the Electron See Model. I mentioned this earlier. Metals have low ionization energies, which means it's fairly easy to remove an electron from them and form an ion. In a metallic solid, what happens is those electrons that would normally be donated to a nonmetal when an ionic compound forms are just kind of pooled with the electrons from other metal atoms. So we think of sodium metal as an array of sodium ions surrounded by this sea of electrons. The electrons are negative, and so they are attracted to the positive ions. The positive ions are attracted to this sea of electrons. So this model explains some characteristics of metals. So metals conduct electricity. It's one of the things they're very useful for. Electricity is a flow of electrons. So electrons have to be able to move. We saw that in a solid ionic compound like sodium chloride, it will not conduct electricity because there are no charged particles that can move. In a metal, a solid pure metal, these electrons are not attached to any one particular atom or ion, and so they can move. And so you can have the movement of electrons from one side of this to the other, and that is electric current. We also observed that metals are malleable and ductile. You hit a piece of metal and you're going to put a dent in it. It's not going to just shatter. So metals are malleable because when you put stress on this arrangement, what's holding the atoms or the ions together is not directional. These are just generally attracted to each other, and so if we push some of these out of alignment, they're still attracted, and so it will just dent. You can also pull metals into wires. Again, you can get those atoms to move relative to each other and still stay part of that solid. That doesn't happen with covalent compounds or ionic compounds. Then let's look real quick at the Lewis structure of ozone. Ozone is an interesting molecule because it's part of what helps our planet to maintain its temperature. So oxygen has a double bond. Ozone has 2 bonds, and there's resonance, and so those are intermediate between a single and a double bond. So let's just draw those real quick. So here's oxygen, and ozone. So Lewis structure just gives a resonance for ozone. Really what it is, instead of a double bond and a single bond, it's like a 1.5 bond. So that's easier to see if we get rid of all those lone pairs. And this is like a 1.5 bond and a 1.5 bond. And just for symmetry, I'll get rid of those valence electrons as well. So in an oxygen molecule, we have a double bond, and in an ozone molecule, we have 2 of these sort of 1.5 bonds. They are intermediate in strength between a single and a double bond. Stronger than a single, weaker than a double. What happens up in the outer parts of the atmosphere is ultraviolet light from the sun comes in, and there's an ozone layer up there. The ozone can absorb a lot of the UV radiation. And the reason it can do this is that the UV light is just energetic enough to break the bonds in the ozone, but not energetic enough to break the double bond in oxygen. So what happens is we get a photon. Oh, that's a really, let me do it this way. So we've got a photon of light, UV light coming in, and it can break one of these bonds. So the result of that then is we make oxygen and an oxygen atom. Well, the oxygen atom is not very stable, and so these are going to recombine and reform the ozone. And so what happens is that a lot of the UV light from the sun is absorbed by the ozone layer. Any questions? I think that's cool.